Trini, how are you?
Fine.
What's your teacher doing now? Finish the syllabus?
No, 25. Last one, subtopic 3.
Subtopic 3, that means almost finished already lah.
Yeah.
Okay,
Oh,
anything?
Che, by the way, right, Che,
Yeah,
I have to thank you, lah, Che.
you are always welcome. You are always welcome.
No, because the video I finished watching the one whole chapter, it helped me a lot. Now I remember a lot of things already.
That's why you need to put in effort. If you don't put in effort, also my wasted effort. I can't help you. You have to help yourself.
I mean, there were that chapter one alone had 6 hours of video, and I like finished it, teacher. It's quite a lot, but I finished it. I copied the notes also one by one and understood it. Lah. I tried out now. When I answer the question, I feel better now, like no phobia already.
Okay lah, good to
Feel more
hear.
better.
Good to hear that. Good to hear that.
Mm.
Good to hear that. It all depends on you, right? You want to do well, you have to put in the effort. And I can do anything. I can do my best to teach you, that's all.
Yes, sir.
Okay, anything you want to ask?
No, teacher. You can go on.
Okay, let's go to checkpoint. I think I will go over to you the exercise. Then after that, we will stop for a 5 minutes break and then carry on with a new subtopic. Okay?
Okay.
Just break the video up lah, so that it's easier for you all to do revision.
Yeah. Okay.
Okay. So these are all the things that you need to remember. Okay. What am I doing? This is quantum physics. We are not doing quantum physics. Why am I doing quantum physics? Hey, we are doing quantum physics, correct? Sorry.
Nuclear physics is the last one. Yeah.
Yeah. Okay, so these are things you need to remember. Okay, these are the others. Okay, is it possible for a beam of infrared radiation to contain greater total energy than a beam of ultraviolet radiation? Explain your answer.
So I can't see your slide, sir.
Oh, sorry. Okay, can see now?
Yes, teacher, now can see.
Okay. So anyway, refer to your book. Is it possible for a beam of infrared radiation to contain a greater total energy than a beam of ultraviolet radiation? Explain your answer.
So this is something to do with the wavelength, like which one has a bigger wavelength than greater
This one is
energy, that one, right?
photoelectricity. Energy of photon. Photoelectricity. If you have reviewed, then you should be able to answer me. That's why I say after I teach you the effective way to review it and answer the question, then that's the way forward for you. You don't have to go and forget everything already and then revise again. That's less efficient. Yep. Which one has a greater frequency? Ultraviolet or infrared? This one you must know first. Yeah, ultraviolet has a greater frequency or infrared. Right? All this must be in your head. It's ultraviolet. Okay, can answer? It's unlikely. Energy of photon is HF and depends on frequency. If both beams have the same intensity, if you use the same intensity, the total energy of infrared is lower than that of ultraviolet. Right? Total energy, you just multiply by n only, depending on the number of photons. Infrared radiation has a lower frequency compared to ultraviolet. Okay. It is possible if the intensity is different. Right? If both have the same intensity, cannot be. If it's different, then it's possible. Because intensity, it is possible if the intensity is different, as intensity depends on energy of photon and number of photons. Low frequency infrared can have greater total energy if there are more photons. Okay. Copy whatever you want to copy for the answer.
Teacher, this copying is too long, teacher. You can go on because I will watch later anyway, teacher.
A metal plate is illuminated with light of given frequency. You better copy. That's the way to remember.
No, I will still watch the video because like copy now, then I'm wasting time. I don't want to waste
Yeah.
time,
When you listen to the video again, make sure you copy. There's one way of forcing into your head.
Yeah.
Preferably, if you don't look at the answer, just review the answer and then write without looking at the answer. A metal plate is illuminated with light of given frequency. Which of the following determine whether electrons are emitted or not? Time of exposure to the light. Yep. The time of exposure important to emission of electron.
Time of exposure, no, it does not emit.
Okay, no. Thermal
B,
conductivity
yes.
of metal.
Yes.
Yeah.
So the answer is yes.
No, we never studied thermal conductivity under photoelectricity.
Oh, so sorry, that is the SEM 1 chapter 11. Yeah. So no, I guess. Yeah. Type of metal, yes. Type of metal, yes.
Okay. Yes. Type of metal determines the work function and thus the maximum kinetic energy. Intensity of light.
Yes.
A metal plate is illuminated by light of a given frequency. Which of the following determine whether the electrons are emitted or not? No. If the frequency of light is below the threshold frequency, no emission is possible. Right? Unless the frequency is greater than the threshold frequency, then yes. But in this case, no. It doesn't depend on intensity. Area of the plate. Yep, area of plate.
Area of the plate, yes.
No. Area of plate determine the number of photon, the number of electron that is emitted, or number of photons falling on the surface. So no. Okay. Emission doesn't depend on the area of the surface. Small surface or large surface, there will be emission as long as you shine your electromagnetic radiation on the surface. When a metal is illuminated with light of a given wavelength, not all of the photo electrons are ejected at the same speed. Explain this phenomenon. Yep. The electrons are emitted with a range of velocity from 0 to maximum. Explain. Why?
Why? Each of them have different wavelength.
No. Forgotten what I teach you already. Electron at surface are emitted with maximum velocity. Electrons further in are decelerated before they escape. Right? Remember, the background environment of the electron is positive ions. So near the surface, if the electromagnetic direction hits the electron will be emitted with maximum velocity. But if it's further in, right, electron also emit with maximum velocity, but it has to travel up to the surface. So the positive ion will cause a deceleration to the electron. Thus, the further in the electron, the smaller is the velocity when the electron escapes. Right? So it depends where the electron is. That's why it got a range of velocity. Okay, anything not clear? Anything you want to ask? If not, let's go to the next question.
Where are teacher?
Okay.
Hey, teacher, I wanted to read back again. Just give me 1
You want to
minute.
read back? Okay. Yes, anything to ask?
So does the further in the smaller, what does that mean?
Further in the electron from the surface, you escape with smaller velocity or smaller speed.
That means barely lah. That means.
It's just decelerating a car. That's all. So if it's if you are supposed to stop at a line, the car is near a line, then it will pass the line. But if it's further away, then it will stop at the line. But if it's nearer to the line, it will exceed the line with a different velocity.
Okay.
So if further in, there's a retarding force on the electron. So as it moves up to escape, the velocity becomes smaller and smaller. Okay,
Okay.
A monochromatic light of wavelength lambda and intensity I is incident on the metal surface. As a result, photoelectrons are ejected at a certain speed from the metal surface. Describe the effect of using a monochromatic light of half the wavelength and intensity still the same. What will happen? Right? That's why I can see that you have not done your homework.
I was watching the other videos. That's why I didn't focus this one yet.
That's why you have to focus this one first. You cannot afford to spend time to study this all over again. It's more efficient if you understand what I teach you and then do your homework. If not, you will have to come and spend time on it, try to understand it again. Important to reinforce it. Okay, it looks like you don't know anything. Right? We are referring to this formula. Maximum kinetic energy equals to energy of photon minus your work function. So frequency, if your wavelength is half, the frequency will double. Right? They are inversely proportional. And the maximum kinetic energy of the electrons will increase, not double. Right? Because that constant there, it will increase. Monochromatic light of wavelength lambda, intensity 2I. What would you expect what is the effect? The same, we are just using the formula to explain. Use the same formula to explain, that's all. Same wavelength, double the intensity. Can or not?
Can change.
Can then tell me the answer? Right? You keep the wavelength constant. You double the intensity, means you are sending in more photon, more packet of energy. Right? Maximum kinetic energy of electron will be the same. Right? Same frequency, same work function. So maximum the same. But the number of emitted electron will increase. That's double. Right? Think of increasing intensity in this case, increasing the number of photon. Okay, monochromatic light of double the wavelength. Same, using the same equation to argue out. Can or not? What is the
Can.
effect? Then explain. I'll double the wavelength. Here I'm keeping the intensity constant now. Double the wavelength, you halve the frequency. Right? Where the wavelength is double, the frequency is half. Maximum kinetic energy of the emitted electron will decrease. Right? This one is reduced, that one will decrease. It's also possible that no electron will be emitted if the energy of photon, right? Because that you have to also make sure that these 2F, and you put into this calculation there, that energy is greater than the work function. Right? That's why we have to qualify it. It's also possible that no electron will be emitted if the energy of photon is below that of the work function of the metal. Okay? The answer is slightly different from your book. The book straight away say no. Right? You have to look at whether the photon energy is less than the work function. Any question to ask? If not, let's go to the next question.
Next question.
Right? Checkpoint 24.2. When radiation of wavelength that is incident on the metal surface as shown in the figure below, the milliammeter falls to 0 at a reverse voltage of 1.32. What is the work function of the metal in electron volt? Okay, how to calculate? Yep, what formula to use? Yep, what formula to use? Refer to your note. You are wasting your parents' money, as I said to you. You're not putting in the effort to learn. Right? We are stopping the electron, so you have to do work. So that is a formula to remember. Maximum kinetic energy equals to EVS. Vs is the stopping potential. And put in your value. You are told right? That reverse voltage is 1.32 volt. The 1.32 volt is the same as electron volt, 1.32 electron volt. Right? You just multiply by E to change it to joule, that's all. So your EK max, like I said, we are just using the formula, it's HF minus the work function as C equals to F lambda. And 1 electron volt is 1.6 times 10 to the power minus 19 joule. Okay, you want to calculate your work function? Right, work function. I'm replacing the F with C over lambda minus your maximum kinetic energy. Right? Taking this across there, taking kinetic across, that's why I get that equation. Then put in your value. Right? That's your H, that's your C, that's your lambda. Right? I use that calculation, it should be in joule. But your answer 1 electron volt, so I divide by 1.6 times 10 to the power minus 19 to get this whole thing electron volt. And then kinetic energy in electron volt is just that. Okay, anything not clear? Likely you see stars, that's why I say it's a waste of money.
Again, what, teacher?
I say it's a waste of money teaching you, your parents' money, because you don't put effort to learn. Right? So yeah, nothing in your head. I teach you, you've forgotten. There's no progress. You have to make an effort to learn. It doesn't take much time to revise what I teach you and try the question. Okay, anything not clear?
Clear, teacher.
Okay, let's go to number 2. Photon of X energy, each are directed onto a photo cathode with a work function Y. A collector, which consists of a plate, is placed close to the photocathode. Write down the expression for maximum speed of the photoelectron emitted in terms of X, Y, and M. Okay, what's the answer? Same, we are just using the same equation, working with the same equation. You can just take the trouble to work with the equation, that equation, that's all. Change it to other symbol, that's all, this equation. What is the answer? Can okay, go back to the equation, that's all. Then energy of photon, that's your X. That's your X. What function is Y? Put in there. So you want to find the maximum speed, replace it with half mv squared. That's all. Then cross multiply, take the 2 up, take the m down, square root it, get the answer. Okay.
Okay.
The stopping potential to prevent photoelectron emitted with maximum kinetic energy at an angle of theta to the photocathode. Right? That's a picture. That's your cathode. Angle theta. That's your maximum velocity from reaching the cathode in terms of E, X, Y, and theta. Any idea how we should do it?
No.
Right, same thing. Your maximum kinetic energy. Right? Now you want your horizontal component. Right? We don't want the slanting component, we want the horizontal component. So that's why we replace the Vmax, Vmax with Vmax sine theta. And square that. Then you want stopping potential. Right? Kinetic energy, maximum kinetic energy there equals to EVS. Then replace that half mv max square with x minus y. Right? So EVS still EVS. Sine square, that's your sine square theta. And then half and Vmax square is your one there. That's all. Then rewrite that. That's your answer. Any comment?
No.
Okay. Let's go to number 3. Minimum energy required to remove an electron from an atom is 13.6. This is called ionization energy. Find the maximum kinetic energy of ejected electron when a 55 nanometer photon is absorbed in the atom. How to calculate that? Calculate the energy of the photon first. Can?
Okay.
Calculate. We are just repeating that. That's why I say the problem with you, you don't want to copy. Then I keep on scolding you. Right? You're just using this formula, that's all. Energy of photon. You don't want to copy, then you don't learn anything. Anyway, I have to complain to your mother again. No choice.
Sir, but I'm watching the video, sir.
What's the point of watching video? You learn nothing.
What do you mean?
I'm working for you. You're paying me to do your homework for you. Okay. Have you calculated the answer?
Yeah, calculating, sir.
You can't learn this way. Just letting me do the homework for you. You have to do it yourself and learn yourself. Calculate the energy of the photon. Then minus the energy of the electron. Then you get your maximum kinetic energy. What is the answer? Yeah, that's all. Using the same equation, the work function becomes the ionization energy, that's all. Right? That's a H, that's your C, that's your wavelength. Convert it to meter. And then the work function, right? For the minimum energy, convert it to joule. That's why I times 1.6 and 10 to the power minus 19. Then get the answer. Right? We want to work with electron volt, then you divide this by 1.6 and 10 to the power minus 19 here, then you get your 9 electron volt. Okay, anything not clear?
Wait, sir, the 1.4 times 10 to the power 18 joule you converted to EV, how much, sir?
This one is in joule. So you want
Minus.
converted to electron volt, then you have to divide by this value, 1.6 and 10 to the power minus 19. All this must be by your fingertips already. That's why I say you didn't do homework, you cannot remember all these things. You got lost. Okay, anything not clear?
Clear.
Okay, try this one. Silicon is illuminated with light of wavelength 220 nanometer, and the stopping potential is found to be 0.85 volt. Is then illuminated with light of wavelength 160 nanometer, and stopping potential is 2.97 volt. Find Planck constant. So use the same, they are just using the same equation, playing with the same equation, that's all. The equation, and that's equals to EVS. That's all. Go and work it out. You should get two equation, two simultaneous equation. Okay, EK max equals EVS, and that's equals to your HC lambda minus W. Right? VS, take the E down, HC over E lambda, W over E, and put in your value. Okay, 0.85. 0.85. Right? No need to put in value for HC. It will disappear in your calculation. HC, and then there's your E, there's your wavelength, that one there. Convert to SI unit, and your work function divided by E. Then second equation, that one. Right? Lambda is that one. You want to find the Planck's constant. So Planck's constant, you just subtract the two equations, 2 minus 1. Okay. Take the common factor out, H and C. H and C, that's your E. Then you got 1 over that, divide by 1 over that, sorry, 1 over that, minus 1 over that, that's all. So work it out, you get your H. And use one of the equation, calculate your W. Okay, I can use this equation. W, take across there, 0.8, take across the other side, right? Take this one across there, that one across there. So you got your W, HC, and your wavelength. Okay, your maximum kinetic energy is just your EVS. Okay, just using this one. W take across there, EK max take across there, or EVS is that one there. Okay, HC as a lambda, put in your value of your H that you have calculated. That one there, put in there and calculate out. Okay.
Okay.
Okay, we'll stop here for 5 minutes. And I expect you to do your 5 and 6. We will discuss that tomorrow. After that, we'll go to a new subtopic. We'll take 5 minutes break.
Okay,